Hello, my name is Susu. I am a research assistant at Polytechnic University of Bucharest, working with Professor Georgi M. Stefan. The idea of my research project is to compile efficiently, time and energy-wise, sequential programs to coordinated vector assembly for a system using the low-power Connex-S vector accelerator. We generate for custom with Connex-S processors vector length agnostic, or VLA, programs which are handled by a JIT vector assembly runtime framework called OPINCAA, somewhat similar to the OpenCL embedded profile. The reason we do VLA compilation for custom width accelerators is Connex-S can save energy if its width, also called vector length or CVL, matches the main running applications, for example for digital cameras of different factory resolutions. Connex-S is an easily scalable open architecture vector processor with a 30-year-old history designed to run efficiently based linear algebra subroutines. Scalability means we can easily change one parameter in the Verilog code to synthesize the processor with a number of lanes between 32 and 4096, which makes the architecture very wide for today's standards. Each lane of the processor contains a 16-bit integer ALU, which is good for power consumption, but we need to emulate the unsupported types. Connex-S has a predictable performance because it has no caches, no speculative execution, and has a separate scratchpad banked vector memory of only 256 kilobytes. This is why we can devise an accurate cost model for the processor. We currently work with a processor synthesized in an FPGA. The compiler toolchain for Connex-S relies mainly on the LLVM framework, but also on the PPCG C-to-C loop optimizer, in case the program memory footprint is larger than 256 kilobytes of the scratchpad memory. We had to implement a new backend for Connex-S, in which we add efficient emulation of arithmetic operations for unsupported types such as 32-bit integer and 16-bit floating point. We also extend the loop vectorized pass of LLVM in order to generate VLA code with OPINCAA coordination calls and perform symbolic quantitative analysis. The compiler generates an OPINCAA C++ program which we then take and compile with GCC to run on the embedded host. We now present the performance of the Connex-S accelerator with 128 lanes synthesized at 100 MHz in a Xilinx Zinc 720 with respect to a dual-core ARM Cortex-A9 with neon SIMD units at 667 MHz, loosely integrated with Connex-S. On the left, we present speedups of benchmarks such as matrix multiplication, filter 2D, used for noise removal in image processing for 3 different array element types. The 16-bit integer, the native type for Connex-S, then the emulator types 32-bit integer, for which we actually don't achieve acceleration, unless we use, for example, a wider Connex-S of 512 lanes. Also, we have a 16-bit floating point type emulated by both Connex-S and ARM. We perform energy measurements for the Zinc 720. We see that increasing CVL saves the energy spent running a benchmark on Connex-S. We consume 45.43% less energy for CVL 128 than for 32 lanes. Therefore, as claimed at the beginning, to be energy efficient, we use a custom with Connex-S accelerator with a CVL close to the trip count of the vectorized loop. Here we show that our i16 benchmarks save energy on the accelerator at least by 1.4 times with respect to the dual-core ARM CPU. It's possible to save 10 times more if Connex-S is produced as an integrated circuit, not synthesized in an FPGA. We invite you to try our open source software tools for the open architecture Connex-S accelerator, including our cycle-accurate processor simulator. Thank you very much for your attention.